So here we're given a population density function in number of people per square mile for a town on an island that it's modeled by this function, where x and y are measured in miles. So a grid is laid over the island in order to determine the population density at different locations, and then based on this, it's how we get the average population here. All right. Well, so, letter A, they're asking us what is the total population inside the rectangular area defined by the vertices 0, 0, 4, 0, 0, 2, 4, 2. All right? So, number one, let's draw the island. So, I mean, like a very generic island, I don't know, like this. And let's impose a Cartesian plane somewhere. All right. So we're interested in the rectangular region comprised by this by this bound right here. That is the origin. What else? The point 4, 0, 0, 2, and 2, 0, 2. I mean, no, 4, 2, and 0, 2. All right. So let's draw this rectangle. So this will be our region R. All right. So let's shade it. As usual, let's shade our regions of integration, and let's label this as our R. Okay. So let's state the domain of integration for this. That is R, which is the set of all order pairs x, y, such that x varies between 0 and 4 and y varies between 0 and 2. So that is our domain of integration. That's going to give us the limits of integration for this double integral. All right, so let's see. So the total population, so we're finding the total population first by integrating this this given function over the given interval. So that is the double integral over the function f of x, y, dA over the region R, where the limits of integration are both lower limits are 0 all the way up to 4 in terms of x and 2 in terms of y. So the density function f of x, y, that'll be 5,000 x e to the y over 1 plus 2x squared. And well, I already put the limit, so I'm going to go dy dx. All right. So in this case, I think we can go dy dx because integrating with respect y, we just integrate the e to the y, which is going to be itself, right? No problem integrating e to the y. Even if we went dx and then dy, then we would have, yeah, it's still possible. It's just a u substitution, right? So let's see about this. So let's integrate with respect y. And again, keep in mind, dy will be related to these limits, and dx, that is the inner limits, and dx, which is the outermost differential, is related to the outermost limits of integration. Okay, so integrating e to the y, which will be itself, that equals the integral from 0 to 4 of 5,000 x over 1 plus 2x squared e to the y itself, right, from 0 to 2 dx. Okay, from 0 to 2 dx. So upper limit minus lower limit as usual, that is the integral from 0 to 4 of 5,000 x over 1 plus 2x squared, that is e to the second power minus e to the 0 dx. So this is just going to be a constant value. That is, okay, actually, along with the 5,000, this will be just a multiple constant. Although, okay, let's think a little bit ahead of the game here. For instance, if I think of the u substitution that we're going to do here, The derivative of 1 plus 2x squared, what is that? 4x? So, how about divide that 5,000 by 4? I'm pretty sure it's divisible by 4, right? So, 1,000 divided by 4 is what? 250. 250 times 5, is that 1250? Is that 1250? 250 times 5? It is, right? Okay, so I'm going to write this as 1250. Oh, wait, no, times 4, rather. It's times 4. What is, it's 1250 times 4? Yes, 1250 times 4, right? So I'm going to write 1250 times e squared minus 1 times the integral from 0 to 4 of 4x over 1 plus 2x squared dx. Okay? So that's because when we do u equals 1 plus 2x squared du equals 4x dx, x dx equals to 1/4 du. All right? So, well, actually, we don't need we don't need this part right here because we already have the 4x dx, right? We don't need any compensation factors there. So, but we still need to change the limits of integration. That is, u of 0 equals 1 plus 2 times 0 squared u of 4. That equals, what's that? 1 plus 2 times 4 squared, that's 16 times 2, 32 plus 1, 33. All right? And that equals to 1. So our new integral here will be 1250 e squared minus 1 times the integral from 1 to 33 du over u, right? And well, this is just the ln rule, right? This is just the log of the basic ln rule. That's 1250 e squared minus 1 times the integral from 1 to 33. Oh, wait, no, just ln of u, absolute value of u, from 1 to 33. Although in this case positive numbers, there is no need for absolute values anyway. I mean, even if we went back substitute with 1 plus 2x squared, we don't need those absolute value bars because 1 plus 2x squared, it's always positive. So those absolute value bars are redundant unless you had a function with, an odd function that outputs positive and negative value, then you would need those absolute value bars, but not in this case. Okay, but I'm just going to write them. So that's 1250 e squared minus 1 times ln of ln of 33 minus ln of 1. ln of 1, we know that's 0, so our final answer will be 1250 times e squared minus 1 times ln of 33. So that is the exact value of the population. But of course, we're not going to report this results, say on the news or on a book or on a statistics, a list of population. No. So we need an approximate result. So this is approximating to the nearest integer. I get 27,924 people. All right. So that is the density in that sector of the island, right? The sector bounded by those points, by the rectangular, it's a rectangular region. Now, what is the average population density for the region defined above? That's the density, but that doesn't tell us how it is, in a way, distributed, right? So that's why we're going to get the average. Well, how do we get the average? Well, so we divide the number of people, the population here by, well, in this case, it's the area, right? So that is really the average value. So let's see. Z bar equals 1 over area of R times the double integral of R of the function f of x y dA. But do we have to compute the double integral again? No, you don't need it. You already have it from part A. All we need is find the area of R, which is easy to find because this is a rectangular region, right? So unless, check this out, unless we were interested in finding, say, the population density given by this region right here, then we would need to know what's the upper and lower function, and then we would have to do another double integral to compute this. But in this case, since the region we're integrating over, it's a rectangular region, just use your knowledge from geometry, find the area of the rectangle given these dimensions, right? So, all right. So 1 over the area of R. The area that is, it's a 4 by 2, right? It's a 4 by 2, so that is 1/8. Careful. That's not 1/8, it's 8 times what you got from part A, which is 27,924 people. All right. Well, simplifying, this is approximately 3,491 people per square mile, because this is a density population. So we need a ratio of units here. So that's roughly how many people live per square mile. So not the actual population. All right? Yes.
Should we use like the exact answer and then divide that?
Exactly. And then
okay. Not
yeah.
Like the rounded one like you did?
No, not really. Yeah.
Okay.
Either way, it's fine. In the end, we will be rounding to integers because it's people. So, yes.
It is going to be total because the area was rectangle, right?
Exactly. But again, if we had a weird and crazy function, well, we would need to know those functions, right? So, say that we're still looking at that island, and I would like to know what's the population that lives inside, the intersection between sine and cosine, right? At any random point. Well, that would be a little crazy. It's not the craziest problem in the world. What would make it just more time consuming is that we would need to find this area right here as a double integral, or even as a single integral using your knowledge from Calc 1. That's still valid. It's again the area under the curve or between the two curves. It's still a result of doing a double integral, so you can save one step, so to speak, by just doing upper minus lower, right, rather than setting up the double integral. So. All right, what else? To wrap up the section, let's have a look at improper integrals. Remember from Calc 2, when an integral converges, diverges, etc. Well, they're coming back with double, and later in a couple of sections with a triple integral. Yep. So. Let's see. The integration rules are not going to change. They are still going to be the same formulas, the same methods. All we need to make sure of is we use the proper notation for an improper integral. Again, for instance, if you integrate e to the 3x, so e to the negative 3x dx, what's that? From 0 to infinity, for instance, right? 0 to infinity. Yes, that's negative 1/3 e to the negative 3x from 0 to infinity. And then what would you do? Upper limit minus lower limit, that equals negative 1/3 e to the negative 3 times infinity minus e to the negative 3 times 0. Well, this is technically not the correct way to denote our work, because we are doing, operations with infinity. Can you add and subtract infinities? Infinity minus infinity. How do you know which infinity is bigger than the other one, right? How do you know the two infinities are equal, right? Well, it's infinity. It's just an idea of something that gets big and big and big and never ends. So we don't know how big it is, right? So instead, a way around this issue here is to denote this using limits, because rather than can I stand at that point, well, we cannot go all the way to infinity, but we can still see what's the trend, where are we approaching to, which is the limit. So the limit notation permits that. So again, This is not how we're gonna go. All right, let's have a look at one example. Anyway, so the integral from 0 to infinity and from 0 to 3 of this e to the 5y over 9 plus 4x squared dy dx. So in this case, we're going to integrate with respect y first. That is the exponential function. That is the integral from 0 to infinity of, well, to begin with, 1 over 9 plus 4x squared times 1/5 e to the 5y, evaluated from 0 to 3. Okay? So, and again, these limits of integration are only for the y variable because we integrate it with respect to y. And don't forget the dx. All right. So let me take the 1/5 outside. 1/5 times the integral from 0 to infinity 1 over 9 plus 4x squared. And that is e to the 5 times 3 minus e to the 5 times 0 dx. So e to the 5 times 3, that's e to the 15 minus e to the 0, that's just 1. So that's 1/5 times e to the 15 minus 1. Integral from 0 to infinity of 1 over 9 plus 4x squared dx. Okay, here is where we need to be careful with our notation, how we set up the improper integral. Okay, so to begin with, again, we can just do operations with infinities. So instead, I'm going to write this integral. So that is 1/5 e to the 15 minus 1 times the limit as b approaches infinity of the integral from 0 to b. Okay, so, and well, at the same time, I'm going to rewrite the expression. I know if you can integrate this in your head, just make sure to know what you're doing. Otherwise, write these two terms as a quantity squared plus another quantity squared. For a big reason, I'll show you in a second. That is 3 squared plus 2x quantity squared under the dx. All right? So we can see the following. That is a equals to 3 and u equals to 2x. All right? Because when we do the u substitution, it's not just going to be an x or something. It's going to have something else. That is du equals to 2dx, where dx equals 1/2 du. We also need to change the limits of integration accordingly. So let me do that here. U of 0, that is, careful because the u, it's not going to be the entire denominator. It's only the quantity whose squared equals 4x squared. That is 2 times 0, which equals to 0. And lastly, u of b, it's simply 2b. That's it. No numbers here. Again, b is what we're setting for the infinity. So we're ready to rewrite this integral in a way that we can identify the form and boom, integrate. All right. So what is that going to be? So number 1, that is 1/5. That is 1/5 e to the 15 minus 1. Integral from, limit as b approaches infinity of the integral from 0 to 2b of 1/2 du a squared plus u squared. Well, I'm going to take that 1/2 and multiply it outside with the 1/5. That's going to give us what? Isn't that a 1/10? Right? So that's a 1/10. So 1/10 e to the 15 minus 1, limit b approaches infinity, integral from 0 to 2b, du over a squared plus plus u squared. And no, don't do a trigonometric substitution. No, someone on the quiz, I think, on one of the quizzes where one of these integrals showed up, did the u substitution. I mean, that's fine if you want to revisit your techniques, if you want to practice on them, that's fine. Just use the formula. In this case, isn't that just the arctan rule? All right, that is, okay, yeah, let's write the whole thing. 1/10 e to the 15 minus 1 limit b approaches infinity of 1 over a arctan of u over a, evaluated between 0 and 2b. Okay, as usual, well, number one, let's back substitute for a and u, and then I'm going to do upper limit minus lower limit. So, well, actually, no need to back substitute, only for a, actually. Or should we? Oh, no, yes, actually, so, that is 1/10 e to the 15 minus 1 limit b approaches infinity of 1 over a, that is 1/3 arctan of u over a, which is 3, for where we integrate between 0 and 2b. Okay, so I'm going to do two things at the same time. I'm going to multiply that 1/3 with the 1/10 outside. That's going to give us a 1/30th e to the 15 minus 1 limit as b approaches infinity of arctan of 2b over 3 minus arctan of 0 over 3. You guys agree it's going to be 0? Okay, so just zero it out, right? Okay, let me make some space. Okay, arctan of 0. Okay, let's simplify all this. Arctan of 0, we know that's a 0, right? That's 0. What about arctan? Well, in this case, we're approaching infinity. So 2 times infinity over 3, it's still infinity, right? We don't know how big the infinity is. Well, what is arctan when it's approaching infinity? Pi over 2, all right? Pi over 2. Okay, simplify. That's going to be simply 1/10 e to the 15 minus 1 times pi over 2 minus 0, which is simply, I'm going to multiply pi times 1, that's pi, and 2 times 10, that's 20 e to the 15 minus 1. Now, we need to discuss the convergence of this integral. Yes? 1/30th? Yes. Yeah. 1/30th. Okay, 1/30th times 2, that's 1 over 60, right? Yes. So, what do we need to write at the very end for this integral? We only say converges, right? That's because, well, we get to a value, right? To a real number, 0, a negative result, whatever that is. But if you get either a d/e or an infinity out because of the limit, then diverges, right? It's the same conclusion as in Calc 2, all right?
Is that really want to do like only convergence and values, or you have to do like conditionally convergence too?
Well, the conditional convergence is when we're working with what's that, with the alternating series test. You know, when you first check the two conditions to determine that it converges, that is, it's decreasing and the limit goes to 0, which is basically the end term test, right? But then you take the absolute value to create a whole new series, but that's for the series, not for the integral, right? Okay.